Hello viewers on YouTube. In this video tutorial, I would like to show you how the sum of the GP formula is formed. So let's begin by considering the general term of the GP. We said for any series to take the pattern of a GP, then that series must be in this form, whereby the first term will be A, the second term will be AR, whereby a product of the first term and the common ratio, and the next one will be AR squared, and continuously like that the index of R increases, then dot 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 all the way to AR to the power of n minus 2, and finally the last term will be AR to the power of n minus 1, which is the general term. Perfect. Now if for instance we want to find the sum of this series using algebra, then what we're going to do is to say that the sum S would be equals to A plus AR plus AR squared plus AR cubed plus AR to the power of 4, then plus dot 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 whichever terms comes in, plus AR to the power of n minus 2, and again plus the last term AR to the power of n minus 1. Perfect. Now let's assign an equation to this equation we are having, because it's absolutely an equation, but we want to target. So let's say it's equation 1. So I have no space on either side in order to write it, but let me put it on top. Now to form another equation, let's multiply both sides of this equation 1 by the common ratio R. So if we multiply S by R, we have SR equals A times R, AR, plus then the next term AR times R becomes AR squared, and this continues increasing like that, AR cubed plus AR to the power of 4 plus AR to the power of 5, then plus dot 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 plus AR to the power of n minus 1. Yes, it should be n minus 1. I'm going to show you that, plus AR to the power of n. Perfect. Okay, so I will omitted a step here which I would like to show it out. Okay, so how did I get AR to the power of n minus 1? AR to the power of n minus 2 multiplied by a common ratio R. This common ratio R is the same thing as R raised to the power 1. Okay, good. Now we can use some of the laws of indices, typically the product law. Understand? Now this A is a coefficient, we can take it, leave it like that. Now R is having the same base, so let's take one of them, then we have to add their powers. Okay, so that will be n minus 2 plus 1, which results in AR to the power of n minus 1. So you might have a question that why did I use law of indices when the coefficient of the two values are not the same? Well, it can be used if the coefficients are not the same. You understand? The goal is that just make sure that the bases are the same before you apply the concept. If the coefficients are not the same, then you apply the normal operation to the coefficient. Okay, so that will be, I did A times 1, which gives us A, because the coefficient of that R raised to power 1 is 1. Okay, so I did the same thing for what's it called, AR to the power of n minus 1. At the end of the day, you get AR to the power of n. Perfect. So now that we have equation 2 as well, what we are going to do now is to do equation 2 minus equation 1, or in other words, we want to subtract equation 1 from equation 2. So this is equation 2. So now let's do, so we are subtracting both sides, SR minus S. Okay, perfect. So now we have SR minus S to be equals to, now there's no A term in this equation 2, so therefore it's going to be 0 minus A. Now notice that these other terms will tend to cancel. Okay, when we subtract AR cancels, AR squared cancels, AR cubed cancels, AR to the power of 4 cancels. AR to the power of 5 will be within this region, which we also cancels out. AR to the power of n minus 1 cancels AR to the power of n minus 1. AR to the power of n minus 2 will be cancels out by something similar to it within this range. So it should be within this range. If you are wondering, in this second equation, if we try to maybe simplify it more forward, we will have a term that will be of this form: AR to the power of n minus 3. Yeah, it will be within this region. You understand? Now we multiply a to the power of n minus 3 with r. It gives us a to the power of n minus 2, which we cancels out what we want to cancel. So the only terms that we don't cancel out is just the first term and this last term. You understand? So therefore, now since there's no last term yet, that will be a to the power of n minus 0. So that will be plus a to the power of n. Perfect. So this equation has become SR minus S equals minus a plus a to the power of n. So right now, let's flip the position of this. We have SR minus S to be equals to a to the power of n minus a. So at this point, let's factor out S at the left hand side and let's factor out a at the right hand side. Then we have S in the bracket of r minus 1 to be equals to a in the bracket of r to the power of n minus 1. So now dividing through by r minus 1, then we have this. So we have the sum of the term to be equals to a multiplied by r raised to the power n minus 1 divided by r minus 1. And this formula is effective if the common ratio is greater than 1. So how do we get the equation for r less than 1? That is when the common ratio is negative or when it's a fraction. You know, we have another formula for that. So how do we show that out as well? Well, I will make that an exercise for you. The only thing you have to do is just that instead of doing equation 2 minus equation 1, do equation 1 minus equation 2. That is, in other words, you can do equation, or you can subtract equation 2 from equation 1. Then you solve it the same process we did to this. At the end of the day, you will end up with the formula for the sum of GP whose common ratio is less than 1. Okay, perfect. So now let's show out the sum to infinity formula. You know, we said for the sum to infinity, S of infinity equals a divided by 1 minus r. And to prove this, we'll be considering using the sum of term for common ratio less than 1. We say for common ratio less than 1, we have a multiplied by 1 minus r to the power of n divided by 1 minus r. Now, since common ratio is less than 1, it means the common ratio can either be negative or fractions that are less than 1. Now, this formula, it won't be applicable for, sorry, I'm talking about the sum to infinity. We can't show it out for a series whose common ratio is negative. So this formula is applicable if that common ratio is a fraction and its absolute value is less than 1. It must not be negative, you understand? So if that is the case, for this one, the sum of term, if the number of term gets more larger and larger, what will happen to r raised to the power n? If r is a fraction that's less than 1, consider 1 over 2. So if we do 1 over 2 raised to the power 2, that becomes 1 over 4. As 2 becomes more larger and larger, then this value becomes 1 divided by a big value. Okay, and 1 divided by a big value becomes or tends to 0. So it means as n tends toward infinity, then r raised to the power n will tends towards 0, because r is a fraction, and when it keeps on increasing the power of a fraction that's less than 1, the result will be approaching 0. So clearly we can say this becomes 0, and we have to sum to infinity as n goes towards infinity. So it becomes a multiplied by 1 minus 0 divided by 1 minus r, which ends up with the formula we got here. So that's how to show out the formula for the sum of GPs, both for when common ratio is less than 1 and greater than 1, and at the same time when the number of terms is approaching infinity. So I hope you find this helpful and understandable. If you haven't subscribed, feel free to subscribe. Thanks for watching. See you in the next video. Bye for now.